previous lecture, I talked about the axial personality or gender congruence. So, following that, today we're going to be talking about flux, or rather, behavioral flux. To be more specific, and this is not magnetic flux that we're talking about. Magnetic flux is denoted by phi. Capital Phi. It's a magnetic flux. We're not talking about that. We're talking about behavioral flux, the fluctuations of the behavior. So, fluctuation or behavioral flux, which is denoted by a blackboard boldface F, is basically the second derivative of the choice with respect to time, which is also equivalent to the derivative of the confidence with respect to time. So is our confidence, C is our decision or choice. So the second derivative of choice is the flux, and this the derivative of the confidence is flux. And I couldn't find a better term to describe flux or the derivative or the change in the confidence of a person, so I'm just going to call it behavioral flux. And there are actually a bunch of equations that relate this guy to other quantities, and one of that is the Flux-W equation. Actually, let me get my notes here. The flux condition equation, and that basically states that the flux minus the derivative of the condition is equivalent to and the flux minus the inclination here. Inclination is basically the derivative of the condition with respect to time. So flux minus this is 0 because we know, from here we can say that the flux is equivalent to that, and flux is also equivalent to the rate of change of the condition. Would you guys agree that if the condition is, if the derivative of the condition is equivalent to the derivative of this, then surely it is equivalent to the flux. The confidence. We established in a previous lesson that the derivative of the condition is equivalent to the derivative of the condition. So therefore, this thing here holds. These equations hold in the previous lecture. And so, it's basically the rate of change. Flux is just the rate of change of the condition. So the rate of change of the confidence. And we have another equation that's the flux. It's an integral equation rather than a differential equation. It's the flux variability equation. You know the variability already. It's the rate of change of the appearance with respect to time. And the Flux-W equation basically states the double integral of flux with respect to time is equivalent to the integral of W with respect to time. And from here, if we just take the differential both sides, we soon find out that W is equivalent to the derivative of the flux. It's W. So the variability is equivalent to the derivative of the flux. And I actually have a proof for this. I have a proof on what is this, how it is, or this equation. Down somewhere in my notes, if I where is that? Oh no, where is it? Where did that go? Where's that? Oh, okay. I can't find it. Let's see my notes. It's supposed to be my notes. Alright. So I think I have a better version. I have a proof here, but I think I have a better version. Just can't find it. It's been a while since I did that proof. So while that as well. Take a brief note of this. Alright, I think I found it. Okay, so here's the proof for the Flux-W equation. Why this integral equation holds. So consider from the previous lecture that the derivative of the condition with respect to time is equivalent to the derivative of the choice with respect to time. Choice with respect to time. So from here we can say that I, or the inclination, is equivalent to O, which is the confidence. And we know that O is the derivative of the condition with respect to time, and that the derivative of O with respect to time is simply the flux. So if we take the integral of this side, both sides, O is equivalent to the integral of flux with respect to time. Just take the derivative of that to eliminate that dt. Take the integral to eliminate that dt. D over dt, and we get O equals integral of f dt. And so from there, this equation here becomes I equals integral of f dt. But I is precisely dc over dt, because dc over dt equals the integral of flux with respect to time. And so c, if we take the integral of both sides again with respect to t dt, this becomes dt squared. This crosses out and we get capital C conditions equal to the double integral of the flux dt squared. And this is basically just envisioned as using boxes to approximate the area under the flux's graph. Instead of using rectangles, we're using squares this time, and like making sort of grid in there, approximating that using the grid by counting the squares, and seeing the limit as they approach infinity gets smaller. And so this since c is equal to f dt, and dc, what was that again? Okay, so dc over dt or dA over dt is equivalent to the wearability. And so, yeah, I don't go back to the original, but we're close. This is actually how the books work. So, yeah, C is equal to A. So we know that the choice is equivalent to the appearance, the notation, and that A is equivalent to the double integral. It's also equivalent to the double integral of f with respect to t. And so, yeah, so C is not this, but rather C. We know that W is equal to dA over dt. Take the integral of both sides, and we get A is equal to the integral of W dt, the wearability. And so, since A is equal to A itself, then this just becomes W dt equals double integral of f dt squared. That is a box to end the proof. Quadrat demonstrandum, what we usually say. So that's the proof for the flux wearability equation. And it's a bit messy, and I end up like improvising it a bit at the end, but that's what it is. So we can actually derive the flux, the F minus I equation, flux minus the inclination equation. So if we take that double integral, or the flux squared, flux wearability equation, dt. So we take the derivative of both sides, and we get integral of f dt is equal to w. And from there, f is equivalent to the derivative of the wearability with respect to time. And F minus I, inclination, so there, di over dt, so F minus I, C, so yeah, I is equivalent, we know that the inclination is equivalent to the derivative of the flux with respect to time. It's such a mess. So from there, we can say that F minus derivative of integral of I dt is 0, and that just gives us our equation. It's I. One of the parameters. So that's it for this lesson. It was a big mess, but I assure you guys that the next one will be cleaner. So the next lesson will be the flux condition equation. It's a different one. It's not like the flux. Oh, actually, we did discuss the flux condition equation. We did both these lectures in just this one lecture. I'm such a crappy professor, if you guys ask me. But we discussed both of them already. So we're gonna skip right over to behavioral diffusion. Or no, dynamic. We're gonna discuss dynamic, which describes the submissiveness or the dominance of a person. So it's Blackboard already discussed it in the notations episode, notations lectures, so you guys should understand what dynamic is or get a gist of it. So that's that. Dynamics next lecture. I'm not sure if I'm gonna be able to upload before Christmas break. When the Christmas break comes, which is on Saturday, 18. I want you guys to enjoy your Christmas break and like don't do the homework. It's alright, even though you're enrolled. Just make sure to submit it by before the end of the school year, which is around March. And make sure to do all your homeworks. I'm not particularly feeling so emotionally well myself right now, but I hope you guys enjoy your weekend and your Christmas break. So I'll see you guys in the next lecture.